Hi friends, now we are into fifth lecture of the first week, whether we call it week or module. So this is the first week, and every week we'll have 5 lectures. So this is the last lecture, and so far we have discussed risk conscious operation management, complex engineering system, role of human factor in risk conscious operations management, common cause failure, and so we saw PRA essential feature of PRA, probabilistic risk assessment, we have discussed in the last 4 lectures, and we came to even estimating the damage state of the plant and the likelihood consequences. Now it's time, if it is the first week, it is time to see a few or 1 or 2 case studies, so that we would like to demonstrate that utility of this approach in the real field actually. There are 2 case studies. First case study deals with the remaining useful life estimation. Every plant after completing its design life, there is a urge to not urge, requirement or regulatory requirement to say that for rest of if we want to extend the life or for life extension, we have to demonstrate that there is still capability in the plant to operate further, maybe 5 years, 10 years, 15 years, 20 years, and this is applicable to most of the plants when they come to the design life completion, and a detailed analysis is required, which is appreciated by the regulator. Then only we will get the extension, point number 1. And then in the plant itself, the operating crew has got some emotion that a particular system we are testing periodically based on the, to begin with you have generic experience data, meetings and all that. From there a feeling comes that this system should be developed, should be tested at least a weekly basis. Now or maybe quarterly basis, that is every 3rd month in a year. So now that was okay, some maturity, some knowledge and expert opinions were available, and we did that. But after operating the plant for certain years, the operating crew gets a feel that whether we are excessively testing the system or we are under testing it. So over testing or under testing. Under testing has a disadvantage that the failures which are latent, for them there will not be opportunity to manifest itself, because that comes during testing only. And over testing has got another consequences, the component starts aging. Okay. So and then there are other aspects also, like when we over test the component systems, it is a training that is available to the crew and more frequent opportunity for learning. But when you under test, the opportunities are less. So depending on the plant scenario, a rational based decision has to be taken, and that will come from the data. Okay. And so once you have that data, the plant has got an urge, let us do a risk modeling and see that if we want to, because every testing requires resources. It requires inventory replacement periodically, but one should not do it, just it should be justified actually. So this PRA or risk conscious operation management, it provides an opportunity to make the case based on the understanding that is derived from the performance of the system and present it to the regulator, okay, we want to reduce the frequency or we want to increase the frequency, whatever, it can go in any direction. So these two case studies which I will be talking about in this, you will find it interesting that whatever we are discussing, they are not in theoretical domain or but they see the ground also. Like for life extension, this procedure has been validated for a plant, and the facility found a very useful tool for even this was a life extension, but for many other purposes. So let us get on to the okay. So since it is a last lecture of the series, if you want to have a better feeling of subject, this is my book published in 2023, Risk Conscious Operations Management, because it is better to talk about it now. If somebody is interested, they can buy it. Otherwise, this lecture also will serve the purpose. Okay, and so okay. So in human factor, there are two ways. One is you understand the human data which comes. We understand the human behavior. Okay, but then there is also a way that how to improve the human factor or how to reduce the cognitive load on the human. One of the approach is understanding the plant in a better way, so that stress level can be let's say if plant changes state from one operating state to shutdown state or tripping state, suddenly there is a urgency on human or operator to identify the situation. Okay, most of the time these situations are something which came last time, before that, or maybe it will be coming in the future. So what happens is online signal will help us to analyze those signal, and if we use artificial intelligence or AI ML approaches, these particular thing in a fraction of say minute or even less than a couple of seconds, it will present the scenario to the operator. Okay, this is this type of event, that is class 4 power failure with the one diesel generator. It is a class 4 complete class 4 power failure. So what will happen is the initial stresses, they are reduced, and this becomes a aid to the operator. Okay, and this type of situation, because here we are trying to reduce the human error, which is stresses on the operator, which are the source of mistakes later on, because the time is less, then there is a human is prone to committing the mistakes. So here similarly, when we take a maintenance decision, if I have a risk monitor in front of me, okay, if I have a risk monitor in front of me, then I can see the risk. If let's say I want to take in emergency one fan out of the service, and that decision has to be made in the technical specification says that okay, if you want to shut down the fan, you have to if you have to shut down the fan, you have to shut down the reactor also. But here it can be demonstrated that if this fan is shut down, the increase in risk level a priori can be communicated to and then either time can be extended or whatever. I mean, there are many ways to optimize the decisions and all, but then if the risk monitor is there, we can make the changes very systematically. So this is regarding transient time or situation where accident is not there, but we talked about anticipated transient without scram for those kind of scenarios. And this is for when systematically we want to do this kind of documentation, and we can work on or we can revisit our technical specification component also, because tech spec also, if we convinced, the regulator might provide the waiver. So with this I will start the case study on risk conscious approach to safety surveillance test maintenance intervention. I told you there are ways. If we do more testing, then it is a stress on the human team which is there. But if you do less testing, less training which is available, and it should not go for reducing the or increasing the risk. So that judgment has to be made. So there should be optimum testing. But suppose if the plant feels we are doing unnecessary testing, more testing, and there are so many arguments which can come to support that. and then we do the analysis, detailed analysis, I would say. So here, like for every change, we require a definition of the problem is required, So let us say based on the 25 years of operating experience, it was felt that safety system testing frequency can be reduced from current quarterly once in 3 months to 6 months. This was simple requirement. Now, if you start working on this, you will see what is the system. You will try to understand. You will try to understand what are the components that are involved. So centrifugal form, valve, motor, common cause failure and all. And for that, since you have been operating for 25 years, you had this failure data also. So these failure data are so crucial that will leverage your decision what you have formulated over here. Okay. And then the reasons are also given. So you can see the qualitative reasons that we gave is no significant deviation has been recorded. The frequency testing has been potential for inducing human error, because testing is nothing but intervention of human crew or the operator or maintainer. So that might leave some failure which might take the system to unsafe state. So that possibility has been talked about. The plant availability can be increased by reducing the frequency. It is straightforward. Less testing means more plant availability. Aging of component due to frequent demand can be reduced, because aging, the components are ages if you do more testing. These things are known, they are available, but how to translate into a robust proposal comes from here. Of course, something can be discussed here also, but like uncertainty, what is uncertainty, how robust the data is, and if we do it, let us go for feedback sync and all that. So any change, it always enters into feedback, that means oversight from regulator, how the things are there. So for 1 or 2 years, and all those things you implement and then you go for. So now for this particular case we are discussing, we have data available with us, performance data of the system, and now we have translated into fault tree, and we got a statement of 5 into 10 to the minus 3. So what are the failure situation that will lead to unsafe failure, or no water at pump suction, injection train failure, recirculation failure, detector and INC common cause failure. So these are the reasons. You had data for this thing, and then you draw, like we did in previous case, we make the inventory. So loss of this particular system was required for coolant, loss of coolant accident, frequency was this much. Now, okay, and then primary shutdown system, secondary shutdown system, emergency cooling system, we got various accident sequences. Okay, so this is a plant model. So together with this create the plant model through inventory, and we have various consequences and their the frequency. Okay, and now in this slide, if you see this is our plant. I have shown a very simplified view of the plant. Our safety system also simplified view. How safety system we are drawing the fault tree. How from process system we are estimating our initiating event, and how we are able to do a parametric study. What will be the per month or month per 730 hours, 1, 2, 3, 4, 5, 6, 12 months. We have done the case. And for now, you have a situation also where they require examination. Like if we talk about ECCS availability, only random failures. See, somebody might give argument that our initial argument that when the every ECCS testing requires a plant shutdown, and that adds to unavailability. So here we have done for 2 classes, only random failure and unavailability due to testing, and availability along with the plant availability during test. So random failure and both. This is random failure only. Okay, that means fault tree, event tree, whatever it comes and all. So this matrix has been generated, and based on that, you can see for yourself here that ECCS availability 1.1 into 10 to the minus 3 and core damage frequency. So this 6-month case appears to be valid, but when I take into account my unavailability due to ECCS that testing period, then we have this probability of ECCS unavailability and then finally I have this core damage frequency, slight you can say increase in availability. And now it is left to the judgment decision from the plant, from the regulator, and they might say no, it should be 5 months, it should be 7 months, it should be, but then we have a crystal clear case, what is the situation, what is our assumptions, and then you can call for a decision which is more rational based than the arbitrary decision. We can go for this change or we cannot go for this change. Now, this is one thing you saw inside the plant, what decision has to be taken. Second case study is very important in the sense that everyone or every industry faces this situation, that whether the plant life can be extended or not. And just arguments will not work here. Here has to be scientific arguments are required, or rational based arguments are required. So this is real time. One case study was done for a irrigator plant, and one paper is there in the public domain. I think it was 2012 or 13, 2011 actually. So this paper was published. So that means this particular work, its academic quality as well as practicality also has been demonstrated. So the case was whether we can extend the life of this risk-based approach to life extension of a cobalt-60 plant. Cobalt-60 is one of the radiation source which is used in the facilities for medical sterilization purpose or food irradiation, whatever, so that the life of the food items or sterilized item can be increased. So this is the case. Now this plant is the core configuration of the plant is like this. This is the radiation source which is there. When you want to irradiate the component, you bring it into this cell. When you want to, when we don't have any load on the plant for irradiation, it goes and sits in the cavity. So it is safe. There is no radiation room, and people can enter the room around this and do maintenance whatever it is required. So this is called radiation cell. Cobalt-60 source is the source here, and then when you want to irradiate the component, then the product or conveyor belt, they enter inside. So and then they get irradiated. The plant require its own ventilation arrangement. Source pit is there. Source pit cooling, the cooling also has to be done, because decay heat or gamma heating gamma is a special radiation that heating takes place when it interacts with the material irradiation cell. So this is the just in nutshell. So just if I give you description, ISOMED is a cobalt-60 based radiation plant. Basic purpose is food preservation, not reservation, preservation. I'm sorry, food preservation and sterilization of medical medical devices. Primary concerns are radiation safety and remaining life of the plant. Regulatory approval is required for further operation of the facility. Okay, and the facility available factor has been dropped. When plants start aging, the availability factor drops. That is one of the major sign that, and this plant also has shown, and they want to rejuvenate the plant actually. And risk informed approach or risk based engineering, now I'll call, it has been developed and implemented, and successfully this plant got extension. Major procedural step was plant fibrillation, developing it, understanding the operation, understanding the plant culture, collection of data from the plant, and professional software environment that was used for developing PRA, frequency of initiating event. So whatever is done for PRA, uncertainty modeling was a very special component of this particular exercise. Development of importance measure, because importance measure will help us in formulating the maintenance requirement of the plant in a structured way, because every plant, if it has to be tested, it is a resource consuming. So you got a very elegant approach for doing this. Identify a component for further, some component they require further analysis. You have to come out of the PRA regime, then you have to send it for testing and qualify it for remaining test period of test year, like cables, wires, electronics. So there are two major categories. There are some life limiting component and there are some replaceable components. Other could be a medium difficulty in replacing the component. So based on if it is a life limiting component, then it has to be attained in a different way, and you have to manage that thing, by putting some extra layer or some repair maintenance. And replaceable component, they are very easy to be replaced, and component which have remaining life and they have difficulty in replacing, those components are very important for aging studies and all that. And finally, you demonstrate through again the study only that this life can be extended, and we are in a very safe domain. There is no threat to safety, and at least at the same time availability, plant availability is increases, that means deliverable also will improve. And this was the case over here when the plant deliverables were also improved. So you can see, as part of PRA, list of initiating events and safety system functions were identified. Probably you can go through your slide and understand safety system availability. We got here estimation we have done using the fault tree approach, and then for fault tree modeling and then event tree modeling, all those probabilities are there. And this is the event tree. Like there also, for power failure situation, 1.9 was the frequency, and then automatic shutdown of the source and manual lowering. So if automatic source is not going down, then manual lowering can also be done. So that is possible there. So manual lowering credibility, like human action, that credibility. And then we saw that there is no stress factor for human. So that's why the probability also was very less, 1 into 10 to the minus 3. Otherwise, for emergency condition, the probability will be of the order of 10 to the minus 2, 10 to the minus 0.1 or 1 also. So source cooling. And then this one, these are the header event, safety system, safety action, and we got the consequences, likelihood over here. And then here you see new element, uncertainty analysis. So mean failure rate was 1.9, which I have mentioned here, and then lower bound and upper bound. That means now we are trying to understand the uncertainty. So according to me, in this lecture, we have covered the crux of the PRA or risk conscious culture and all, and so we have provided upper bound and lower bound. So we have 1.24 to 2.66. 1.24 is lower bound, 2.66 is upper bound, and 1.9 is the median value or mean value. And that is possible when we use the chi-square method to estimate the probability and frequency and provide the upper and lower bound. So this is part, what you are seeing over here is uncertainty characterization. It is easiest way to understand the uncertainty and its characterization. And normally result should be declared with this, because point value is not possible. You do some job today and tomorrow the value will change. But if you provide the uncertainty bound, you will be always remaining in the region, in that region, and that way is more acceptable, because randomness is part of any situation that we do. Then safety critical systems were identified, whatever codes they have to do. And then here we have identified safety critical electrical system. So it was first, it was remaining useful life prediction was done, and then that formed the basis for next 10 years. And now I am sitting in another, that means next 10 years I have started, and the plant again requires a qualification. It was same approach being used for another 10 years, because the plant was, as I told you, paper was in 11, 21 it completed 10 years, and now we are into 20s and we want to go to 30s. So one more thing is required, but the procedure remains same almost. And the RUL prediction has been done, you can go through it. And then the radiation consequences, risk levels, how they are, their sensitivity analysis was done, if the criteria is this, and then finally exposure probability, risk profile of overexposure also was developed. So that means consequences, this we are ozone layer formation or this thing. So consequences and likelihood came from probabilistic risk assessment, and consequence evaluation requires a radiation protection knowledge and all, and that's what it was done here. So now if I have to give a conclusion on this first week, okay, why we are talking about risk consciousness? Why? Because the history of accidents have shown in many fields that human factor is one of the contributing factor, major contributing factor to the accidents, and this the contribution is ranging from 50 to 90%, something like this. So that means human factor requires more attention, and if you have to understand the human factor, the cognition, consciousness, conscience, because conscience, why it has entered, because now we are talking about even the security also. So, plant safety and security, these two things together they provide, and so we have to do security risk and safety risk. Safety risk is, we call it as a random failure. Security risk is deliberate attempt. So, this is an era where we need to consider, go beyond cognition and have a concept of our human reliability model should develop for safety and security both. Human factor is central to the enhancing safety and the role of AI/ML. So, now that is one thing, that is estimation or understanding, but if you, there are some deterministic provision by which you can reduce the human failure, like you put an operator support system, which I gave you example, artificial neural network machine learning model, wherein it can identify the transition, it reduces the stress, and stress is the cause in the human also, stress factor is the cause for causing. So, the model should be based on human risk stress ratio on human. Time is one of the reason, but sometimes complexity of the situation could be something else. Even though time is available, we take time to understand that. So, let us make that as a stress ratio as the basis for understanding human power. And PRA provides a very good approach through risk-based and risk-based engineering. We are able to create this RCOM model in the plant. And from there only risk-conscious operation management has come, or as a subject has been developed. It's a new subject. It's a new subject. One is free to because it has entered into engineering. It is not an approach. It is a proper subject science. So here we can say risk-based approach provides a very effective mechanism for residual life estimation or for any changes in the plant. Those two case studies, and there are many case studies. I can go on and on presenting those studies, but those this is a introductory week, and we will discuss more and more as we grow from module 1 to module 2 and to module 12. There are total 12 modules for this course. Thank you.